So section 2.4 about undetermined coefficients. So in this section, we will solve a higher order linear non-homogeneous differential equations with constant coefficients. Unlike what we did in the previous section, we solve equations where the right-hand side of the differential equation, g of x, in this case, was 0. That's what makes it a homogeneous differential equation. Not this time. This time, we're going to have some function that's actually going to make the problem and the situation model even more interesting because, well, think about a first order differential equation. So that's the derivative plus potentially the original function. You can think of, I don't know, maybe the velocity plus position equals some function. If it's 0, well, what do we have? We have a stationary system, right? There's no velocity, there's no acceleration, there's nothing. So here, this function g of x, typically we call it the forcing function. Whoops. It's like whatever speed, velocity or acceleration equals to something, some input or forcing or input function. All right? Okay, so there's two things we need to do here for an equation like this. So actually, we're going to split the solution to the differential equation into parts. What we call y sub c, which at this point you guys know how to solve. Set the differential get the characteristic equation or auxiliary equation, set it equal to 0, and check for the different cases, linear, real non-repeated, real repeated, or complex solutions. By the equation, and then we need a second function that we're going to add. That is what we call a yp, or y particular. Well, that particular solution will depend on what we have on the right-hand side of the differential equation. All right? So there's two parts. The complementary function, which is related to the homogeneous, and the particular solution, which depends on the non-homogeneous side of the equation. Okay, so what about this? So to get the solution to the particular part, the y sub p, the second part, we need to make an educated guess. Well, actually, I'm going to show you the guidelines of how we are going to get that guess. It's not just guessing. There's actually something we're going to follow. All right? And that's going to depend on the input function, on the form of the input function. Well, number one, these are the limitations. This method has limitations. Okay? These are limitations. This method only works for higher order differential equations with constant coefficients only. All right? Number two, g of x can be only a constant, a polynomial. Okay, let me highlight them. Okay, can be only a constant. Okay, can be a polynomial, can be an exponential function, can be sine or cosine, or sums of products of the aforementioned functions. All right. So this method doesn't work for logarithmic functions, doesn't work for reciprocal function, rational function, doesn't work for tangent, doesn't work for arcsines. We're going to look at another method in the next section called the variation of parameters to solve equations where the forcing functions are something other than the ones permitted in this method, the undetermined coefficients. Okay, so the question here is, how do we guess that forcing, the form of the forcing function? Well, number one, so let's say the right-hand side of the differential equation is just a number, like the number a, like the number 5, or maybe 7, maybe pi, maybe e, whatever. Okay, the form of yp is just a constant a. That's all it is. Let's say what we have on the right-hand side is, maybe a linear function like 3x plus 5, all right? Or maybe just 7x without the constant term. Well, even if we're missing a term, we need to write the generic linear polynomial along with its corresponding constants. Let's keep increasing this. What if you have a second degree polynomial? Notice in this case, 8x squared minus 1 is missing the linear term. That is the term having the power, the x to the first power. Well, the form, let me actually highlight this, So, the form of the guess would be the entire generic quadratic polynomial. Let's say you have a cubic, like 7x cubed minus 4x plus 2. Again, notice in this case the x squared is missing. We still need to write it in the generic form. We need to write the entire function here, the entire polynomial. Now guys, here is the thing. Here's the tricky part when we have trigonometric functions, like, by the way, limited to sine and cosine for this one. Okay, so because I can remember how we solved this homogeneous one. We always wrote the solutions having pairs sine with cosine. So sine and cosine will always travel by pairs. All right. So if you have sine 3x, for instance, then you have to have a coefficient multiplying the cosine, and then another coefficient multiplying the sine having the same angle. Same if you have cosine. Same if you have cosine of another angle, cosine 2x. These two travel by pairs, all right? Okay, what about exponentials? So we also mentioned exponential functions, like in this case, like e to the x, okay? E to the some number times x. Well, notice what do we have multiplying e to the x right here? Isn't that just an invisible one? It could have been a 5 e to the 7x, or okay, let me write them down. It could have been maybe 5 e to the 7x, maybe a 3 e to the 7x. So what I'm trying to say here is, what do we have multiplying with the e to the x? Isn't that a polynomial of 0 degree, which in this case it's a constant? Well, so this will correspond to a constant here. So a constant times the exponential. What if we have a linear function multiplying with e to the 7x? Okay, the same e to the 7x, or maybe something that looks like, I don't know, maybe simply x e to the 7x. All right? Well, in this case, we have a linear function multiplying with the exponential function. So, linear times exponential. Linear times exponential, the guess of the particular solution would be a linear containing all its terms times the exponential. Keep increasing the power. So notice for the quadratic times the exponential. Okay, check what happens here. So quadratic times exponential. But in this case, again, we need to include the entire generic quadratic polynomial. Despite in our problem we may just have the quadratic term only without the linear term or without the constant term. We need to put the whole thing. All right? Okay, let's make this even more interesting. What about a combination of an exponential with a trigonometric? Well, so again, regardless of which one, sine or cosine, do you have, you need to include the whole pair sine cosine. For instance, in this case, notice exponential times sine. What do we have? Exponential times sine, exponential times cosine. However, what do you see being multiplied with the exponential? Nothing, so to speak, but there's an invisible one. That one, it's a constant, right? It's a constant polynomial or degree 0 polynomial. That's why we also have this All right, so here we have that constant multiplying the exponential cosine, and then another constant multiplying the exponential sine. What if this time we have a polynomial times a trigonometric, just like sine or cosine? Well, quadratic, okay? Let me actually use two colors for this one. Okay, so for the quadratic, we use the entire generic quadratic polynomial. And for the trigonometric, again, make sure to make them travel by pairs, all right? They do travel by pairs. Do you guys see the pattern here? Do you see? Okay, well, I mean, right now it's like a lot of information. We're going to do pretty much an example of each, okay? So let me just go all the way to, well, what the hell? Let me do the other two, all of them. Okay, so linear, 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 all right? Exponential, exponential, exponential. But why do I have two of them? And the reason we have two of them, that's because we have a trigonometric, and trigonometric ones have to travel by pairs, all right? And something like the worst case scenario, like a monster type of problem where we would have to determine how many undetermined coefficients, okay? Well, so again, here, cubic, cubic, another cube, twice cubic because of the trigonometric, because they travel by pairs, okay? And e to the x, 4x rather, e to the 4x, and sine and cosine, the responsibles of having all these many, all right? So guys, how about we look at some examples? Okay, so let's see all this in action. Okay, so example number 1. Solve the differential equation below. Y double prime plus 3y prime plus 2y equals to 8. Okay, forget about the right hand side for now. All right, so let's solve the related homogeneous equation first by writing the characteristic equation m squared plus 3m plus 2 equals to 0. Well, it seems like this one is factorable by the double bubble method, m plus 1 times m minus m plus 2. All right? This means m equals to -1 and m equals to -2. All right? Given the nature of the solutions, which are real and distinct, we can simply write y equals to c1 e to the -x plus c2 e to the -2x. However, guys, here you need to be very specific about what we obtained so far. This is not just y. This is y subscript c. All right, the complementary solution, or the solution we get out of the characteristic or out of the homogeneous equation. All right? Okay, so now let's have a look at what we have on the right-hand side of the differential equation. Let me actually highlight it. So we just have the number 8, right? That's only the constant function. Well, what was the guess of the form for a constant function? Wasn't that just a letter? Just a letter that represents a constant? Well, number 1, let me use a different color for this. So, y sub p will be of the form simply a. Okay? I'm going to find as many derivatives of the guess as we have in the differential equation. And in this case, it's all the way to the second derivative. Y prime of p sub p equals, well, the derivative of a constant is 0. Y double prime sub p equals, well, another 0. Okay? What are we going to do? We're going to substitute all of this into the given differential equation, and we're going to equate coefficients. Guys, remember what you did in partial fraction decomposition? In cases where you had like the quadratic repeated, you had to like expand the whole thing and then equate coefficients. Well, that's essentially what we're going to do here. Well, this one is going to be a very baby example, all right? Well, so let's go back and substitute into the differential equation. Substitute into the DE for short, the differential equation. Well, what's y double prime? Isn't that 0 plus 3 times the first derivative, that's also 0, plus 2 times y, which in this case is a. Let that be equal to 8. All right. Well, of course, the first two terms are going to go to 0. That's going to leave us with simply 2a equals to 8, which tells us a equals to 4. All right. So this means, y sub p equals to 4, right? Y sub p equals to 4. And we're essentially done with the problem. Now we're going to write the general solution to the differential equation. So y equals to y sub c plus y sub p, which is c1 e to the negative x plus c2 e to the negative 2x plus y sub p. But what's y sub p? Plus 4. And that is the solution to the DE. Well, this is like the cheesy example, like the easy example, right? Because a lot of zeros, but these ones are gonna get interesting, All right. Well, let's actually turn that forcing function into that we had as what was that? It was a constant. Now let's turn it into into a linear function. And well, guys, to save time, I'm going to use the same differential equation for this set of exercises. What changes, it's just the form of the forcing function or the input function just to help us save time. I mean, at this point, you guys know how to solve these homogeneous differential equations. Just know your factoring techniques or the rational root theorem, whatever it takes. So that's going to help us save time. Okay, so number one, actually, I would like to state, okay, let me write y sub c equals to same solution. c1 e to the negative x plus c2 e to the negative 2x. Okay, what would be the form of y sub p? So the form of the particular solution will be, because it's a linear, I'm going to write the entire linear generic polynomial with undetermined coefficients to be determined. Okay, so let's take again two derivatives. That is y prime sub p, that'll be the derivative of ax, it's a, plus the derivative of b, that's just 0. And then the second derivative of y sub p would be the derivative of a constant, which is 0 in this case, right? That's 0. All right, well, what are we going to do? We're going to substitute this into the differential equation, okay? So I'm going to substitute y double prime into the second derivative, but actually this is going to be, again, a 0. It may be irrelevant to write down that 0, but I'm going to do it just so you can see where it goes, all right? Plus 3y prime, which is a, plus 2 times y, which is ax plus b. Let that be equal to the input function, which is 4x plus 5. Okay. Okay, let's work our way through the left-hand side of the equation, simplify, combine, etc. So, what about it? Okay, so this is simply 3a plus 2ax plus 2b equals to 4x plus 5. All right. Okay, guys. Here is where we need to put terms together. So notice how we have terms with undetermined coefficients containing x and some other terms containing undetermined coefficients without any x's. Well, let me actually highlight them for you. So I'm going to highlight with green the constant terms, and I'm going to highlight with yellow the variable, the one that is multiplying with the x. Okay, so I'm going to go to ax plus, I'm going to open parentheses, 3a plus 2b, and then equals to 4x plus 5. All right? Okay. To determine the values of these coefficients, I'm going to equate the coefficient by powers. Check this out. So I'm going to use the same colors. So whatever is multiplying the x to the first power on the left-hand side, set it equal to whatever multiplies x to the first power on the right-hand side of the equation. That's going to give us one equation to solve. That is 2a equals to 4. All right? And on the other hand, so what did we do here? Set this guy equal to that guy. Secondly, I'm going to do, using the same green color, 3a plus 2b. Do you guys agree 3a plus 2b, it's just another constant? So constant equals another constant. All right? The principle behind this is, in order to have an equation, in order to have a true statement with this equation, is the coefficient of x to the first power on the left-hand side must be equal to the coefficient of x to the first power on the right-hand side. And the constant on the left-hand side must be equal to the constant on the right-hand side. All right? So this means, using this green color this time, 3a plus 2b equals to 5. All right? Okay, let me solve the first equation, because the first equation is one variable. The second equation is two variables. So by solving the first equation, which gives us a equals to 2, we may substitute here to find the value of b. All right? So 3 times 2 plus 2b equals to 5. So that is 2b plus 6 equals to 5. 5 minus 6 equals to -1. And b equals to -1/2. All right? So we just determined the values of the undetermined coefficients for this case. Okay, now I'm going to go back to y sub p with generic coefficients a and b. Let me write it down below. So now we have y sub p equals to a, which is 2 times x minus 1/2. All right? And now we're ready to write the general solution to the differential equation, which consists of y sub c, okay, y equals to y sub c plus y sub p equals to what we had already, c1 e to the negative x plus c2 e to the negative 2x plus y sub p, which is 2x plus minus 1/2. All right? Okay. Now let's do the same differential equation, the same homogeneous differential equation. However, the input function, that is the right-hand side of the differential equation, would be a second-degree polynomial. Well, so yes, buckle up for this one, because it's going to be quite a ride, this one. All right? Okay, so what do we have? Okay, so again, y sub c equals c1 e to the negative x plus c2 e to the negative 2x. Okay, because of the space that I'm going to use for this big problem, I'm going to write the guess of y sub p just below this equation, this function here. That is y sub p. Now, what do we have on the right-hand side? Quadratic. So the form of y particular will be a generic quadratic function, ax squared plus bx plus c. All right, we're going to find as many derivatives as in the differential equation for all of these, almost all of these exercises, 2 derivatives. So y sub p prime 2ax plus b, and y double prime sub p equals 2a. Okay? All right. Yes, okay, so let's substitute all this madness in the differential equation. So, what do we substitute into the second derivative here? 2a. Okay, let me change colors. So, 2a plus 3 times the derivative, the first derivative. What do we have for the first derivative? 2a x plus b plus 2 times, all right, y, the generic polynomial without being differentiated, ax squared plus bx plus c. And let that be equal to, in this case, the forcing function, 2x squared plus 4x plus 5. All right? Yeah, again, buckle up. All right? So, 2a is just 2a here. Let's distribute 3 times 2a, 3 times b, that equals 6ax plus 3b. Another distribution, everything in the last group of parentheses just multiply by 2. That's 2ax squared plus 2bx plus 2c equals to 2x squared plus 4x plus 5. Okay. Now let's group constant terms with linear terms with quadratic terms, because that's what we're going to have this time. We would need to equate a constant term with a constant term, a linear term with a linear term, and a linear coefficient with a linear coefficient, and a quadratic coefficient with another quadratic coefficient. Okay, I'm going to use different colors for this again, okay, to help you out with this. So, by the way, is there anything to combine like terms? Actually, there doesn't seem to be anything, all right? There's nothing here. So let me highlight constant term, another constant term, and then another constant term, okay? Use a different color for the linear ones. Okay, that is the ones that multiply x to the first power, and we have one quadratic one. Only one quadratic one. Okay, let me use the same colors actually. Oh, wait. So the quadratic equals the coefficient of the quadratic. The linears, okay, well actually let me save this for later. Hold on. Okay, so what I'm going to do here is check. So 2ax squared plus, okay, look at the yellow one. So I'm going to factor x from these two terms highlighted with yellow. So this will be 6a plus 2b, then multiplying the variable x, plus all the constants, 2a plus 3b plus 2c. Let that be equal to 2x squared plus 4x plus 5. All right? Here we go. Coefficient of quadratic equals coefficient of quadratic. Coefficient of linear equals coefficient of linear. Coefficient, or rather constant term, equals to constant term. All right? Well, let's write the system of equations this gives rise to. All right? So number 1, 2a equals to 2, and with this, a equals to 1. All right? Number 2, 6a plus 2b equals the coefficient of x to the first power on the right-hand side, which is equal to 4. Actually, we already have the value of a, so we can use the value of a from before. 6 times 1 plus 2b equals to 4. Well, subtracting 6 times 1, which is 6, that's 2b, equals to 4 minus 6, is that equal to negative 2? And b equals to negative 1. Well, actually, I'm going to need some space. No, that's good. Okay, lastly, what do we have? 2a plus 3b plus 2c equals to 5. So, well, that's one equation, 3 unknowns. But the good thing, again, we already have a equals to 1 and b equals to negative 1. So, how about, so 2 times a, which is 1, plus 3 times negative 1, plus 2c equals to 5. So this is the same as saying 2c. What is that? What does that reduce to? Okay, 2 times 1, which is 2, plus 3 times the negative 1, which is negative 3. That's 2 minus 3, which is negative 1, so minus 1. All right? Is that equal to 5? So 2c equals to 6. And then from here, c equals to 3. So we just found the undetermined coefficients by equating the coefficients, of course. All right? We may go back to the very generic form of y sub p. I'm going to go and rewrite it like y sub p equals a, which is just 1, so that's simply x squared, plus b, well, actually it's minus x plus c, and then plus 3. Okay? And at this point, we're ready to write the general solution to the differential equation, which is, again, given by two parts. Number one, y equals the y sub c, which is the solution we get with C1 and C2 for the homogeneous equation, plus y sub p, which is what we just found. All right, y sub p, let's see. So this is equal to C1 e to the negative x plus C2 e to the negative 2x plus this quadratic polynomial, x squared minus x plus 3. Final answer. Right? All right. So guys, as you can see, it's a lot of writing. It's a lot of bookkeeping the terms. The calculus involved is only the derivative when differentiating the generic form of y sub p. I mean, just to like recap on what we did. And guys, just be careful with the distributions. Be careful with the signs. That's why I'm color coding all of this, so I can easily show you how I keep track of this. Because one mistake on a distribution or a sign, well, you get to a situation where the problem may not be solvable, or you're going to get into something weird, like something we're going to get later. So careful when solving this. All right. Okay. So for example, letter D. Okay, letter D. The same differential equation with the same y sub c. Okay, y sub c equals to C1 e to the negative x plus C2 e to the negative, what was that, 2x, right? Negative 2x. Okay, what do we have on the forcing function this time? Isn't that an exponential function? Now, keep in mind what you have on the exponential function. In this case, there's apparently nothing being multiplied. Well, it's an invisible one, which is a constant. So, when it comes to guessing the form of y sub p, that'll be some constant multiplying e to the 3x. Alright? Alright, well, let's find the derivatives. Y sub p prime equals 3a e to the 3x. Y double prime sub p equals 9a e to the 3x. What are we going to do? Substitute this 3 into the differential equation. Again, whatever corresponds in the second derivative, whatever corresponds in the first derivative, and whatever corresponds in the original function. Okay? So, let's do that. So, let me use, okay, change color. So, the second derivative, which is 9a e to the 3x, okay, plus 3 times the first derivative, which is 3a e to the 3x, okay, plus 2 times the guess of the function y equals to a to e to the 3x, not 2x, 3x. And let that be equal to e to 3x, which is the forcing function. Well, guys, in this case, it seems like all of these are going to be like terms, right? So 3 times 3, is that equal to 9 plus 9? Is that 18? 18 plus 2, is that equal to 20? A e to the 3x equals e to the 3x, okay? And, well, actually from here, equating the coefficients, I'm highlighting the invisible one, okay? So I know there's not a 1 in there, but it's there in spirit, okay? So I'm summoning the spirit by highlighting it. So 20a equals to 1. That means a equals to 1 over 20. So only one coefficient with an exponential for this one. Not like the previous one, the quadratic, which was kind of an interesting one to do. Okay? So we may go back to y sub p. So y sub p equals 1 over 20 e to the 3x. And at this point, guys, we may go ahead and write the general solution to the differential equation, comprised by a combination of the solution to a homogeneous equation, denoted y sub c, plus another function for a particular solution related to the forcing function y sub p, which is c1 e to the negative x plus c2 e to the negative 2x plus 1 over 20 e to the 3x. Okay? Alright, so that's another example. What do we have so far? One in which the forcing function is a constant. Then we have, what else do we have? A linear, a quadratic. Now we have an exponential. Okay, let's flip the page. Let's go to the next page. Now we're going to have a forcing function in the form of cosine. Let's see how that one works. Okay? All right, yeah, this one is going to be a big one. Okay, so the solution y sub c. Y sub c equals to c1 e to the negative x plus c2 e to the negative 2x. Again, I'm using the same differential equations. All I'm doing is changing the forcing function. Okay? Now, what do we have? On the right-hand side of the differential equation for the forcing function, we have a trigonometric function cosine. Okay, so let's write y sub p, which is in this case a combination of both sine and cosine. Cosine and sine doesn't matter. So a cosine 2x plus b sine 2x. Okay. Well, let's find the two derivatives of this function. Okay, so this will be the first derivative, y sub p prime. That'll be negative 2a cosine 2x plus 2b sine 2x. Okay, and y double prime, y sub p double prime, that'll be, let me make some room in here. So just take the second derivative of this. So that'll be, actually this is sine, right? And what happened? I didn't differentiate really, right? Cosine, there you go. There you go. All right. And well, now let's take the derivative. So that'll be negative 4a cosine, yes, I'm differentiating this time, and minus 4b sine 2x. All right? Cosine and sine. Yes, cosine and sine. Okay, so let's substitute all of this into the differential equation. And guys, it's going to be big. This one is going to be really big. Okay? So, the second derivative, well, verbatim here. The same thing. No multiplication by any constant. So, that's simply negative 4a cosine 2x minus 4b sine 2x. Okay, plus 3 times the derivative, which is negative 2a sine 2x plus 2b cosine 2x plus 2 times the generic form a cosine 2x plus b sine 2x equal to the forcing function. All right, equal to cosine 2x. Okay, let's set this. Let's simplify all this. Okay, so if there's nothing for the first two, just copy them. Negative 4a cosine 2x. Okay, minus 4b sine 2x. Okay, careful here with signs and the distribution and the coefficients. So minus 6a sine 2x plus 6b cosine 2x plus 2a cosine 2x plus 2b sine 2x. Let that be equal to cosine 2x. Okay? Alright guys, so at this point, well, I'm going to combine like terms, if you will. So I'm going to group sine terms with sine terms and cosine terms with cosine terms as follows. Number one, let me highlight them first. Okay, so cosines. Cosine, highlight the cosine, highlight another cosine, and highlight another cosine. Okay, and we use a different color for sine. Sine, sine, and sine. All right. So what about, okay, let me write the cosine 2x. Okay, cosine 2x, and I'm going to open parentheses for whatever we have. Okay, so actually check this out. For negative 4a right here plus 2a, that's actually negative 2a. Do you guys agree? Negative 2a plus 6b. Okay, plus 6b times cosine. And for the sine function, sine, okay, negative 4b plus 2b, that's actually minus 2b minus 6a. Okay, sine 2b. Okay, and let that be equal to cosine 2x. All right. Now here is the tricky part about equating coefficients when we have combinations of sines and cosines. So notice our forcing function only contains a cosine, right? But actually the sine function on the right hand side is, well, number one, okay, before doing this, do you guys agree with an invisible coefficient of cosine, visible one? So this will be, this will be negative 2a plus 6b equal to 1. But what do we set the second coefficient equal to? Because we don't have a sine term. Well, the sine term is there in spirit, of course, plus. You may not see it, but it's there. Plus sine 2x, except that we're multiplying this by 0. All right? So, whoops. Negative 6a minus 2b equal to 0. All right. Let's solve the system of equations. What do we have? Okay. So this is going to give rise to a system of two equations with two unknowns, or rather, like negative 2a plus 6b equals to 1, and negative 6a minus 2b equals to 0. Okay? So that is our system of equations. In this case, we didn't get like one equation with one letter to like do some sort of back substitution. No, we need to solve a 2 by 2 system. And again, there's a few strategies we can use to solve this linear system. You can use Gauss-Jordan elimination, you can use substitution, elimination, determinants, whatever. However, actually, the fact that we have the second equation equal to 0, that's actually very useful to solve for B. Okay, negative 2b equals to negative 6a. Why am I solving for b and not for a? Because if I do for a, I'm going to get a fraction. No, I don't want to get a fraction, at least not now. So b equals to division on both sides by negative 2. Is that equals to 3a? Okay. And then what do we do? Substitute this guy. Okay, I'm going to use a different highlighter here. Okay, let me use, yes, this one. Substitute b into the first equation. All right, so that's negative 2a plus 6 times, actually, wait, that was positive, all right? And that's negative, right? Yes. So 6 times negative 3a, all right? And that equals to 1. Now we have an equation for a rather, so that is negative 2a minus 18a equals to 1, negative 20a equals to 1, so a equals to positive 1 over 20. Another 1 over 20? What, negative 1 over 20. All right? With this, we can get the constant b, negative 3 times negative 1 over 20, which is positive 3 over 20. All right? So here we go. Now we may go ahead and write the generic form of the solution. All right? Well, so 3 over 20, 1 over 20. Okay, so this is, in this case, let me go back to y sub p. Y sub p will be a, which is negative 1 over 20 cosine 2x. Is that supposed? No, that's a positive. That's fine. Plus 3 over 20 sine 2x. All right? And now we may go ahead and write the general solution to the differential equation. So, y, which is y complementary plus y particular, where y complementary is still c1 e to the negative x plus c2 e to the negative 2x minus 1 over 20 cosine 2x plus 3 over 20 sine 2x. Final answer. Okay, final answer. What do we have so far? So far, again, a constant, a linear, a quadratic, an exponential, a trigonometric. Let's have a look at a more interesting one here. All right. Okay, so the next example here, again, using the same function. I mean, the same equation on the right-hand side. Let's see. How did I do this one? Wait a minute. I believe this is a different equation, right? Okay, actually, yeah, let me do a different equation. So m squared minus 2m minus 3, let that be equal to 0 by factoring m factors of negative 3 that add up to negative 2. I guess there's a 3 and 1. However, the signs, what about the signs here? Minus 3 and plus 1. So m equals to 3 and m equals negative 1. This means y sub c will be c1 e to the, what is that? E to the 3x plus c2 e to the negative x. All right? Yeah, that's another equation. Forgot to change it actually to keep it the same. Oh no, I know why I have this equation. Okay. Okay, guys. Now let's let's get to the fun part here. Okay, let's get to the fun part here which is to analyzing the forcing function, which is actually check. What about this 4x minus 5? Doesn't that look like linear? However, what about the second term? That's a linear times an exponential, all right? Okay, check. Linear times exponential. Okay, so what's going to be the form of the particular solution? Okay, let me write it down. Okay, so for okay, let me actually use the space right here. Okay. Whoops. So y sub p will be a generic linear polynomial ax plus b. Okay. And then let's take into account the product between the exponential and the linear plus another linear cx plus d times e to the same exponential 2x. All right? Let's find the derivatives. Let's take the derivatives. Okay, so the derivative of ax plus b, that's y prime sub p equals to a plus the derivative of b, which is 0. And, okay, what about the derivative of, okay, with respect, okay, here we're going to use the product rule. The derivative of the linear cx plus d, which is c times the exponential e to the 2x plus the derivative of the exponential, which is, let me do it here, e to the 2x times 2, but I'm going to write the 2 in the front and multiply cx plus d here. All right? So that's the product rule in action for this one. And that's just the first derivative. We still need to get the second derivative. Okay, let's get the second derivative. All right, so y sub p double prime equals to the derivative of a plus c e, the derivative of c e to the 2x, which is 0 and 2c e to the 2x. And here, we're going to need another product to differentiate. All right? Okay, so what do we have? Okay, the derivative of... how do I do this one? All right, so how about the derivative of the linear expression, the derivative of cx plus d, which is c. Let me leave some space. C times 2e to the 2x, 2e to the 2x, plus the derivative of the exponential only, which is, what is that? Itself the exponential e to the 2x, but by chain rule, we need to multiply by 2. But that multiplication with that derivative of by chain rule, which is 2 times this 2, makes this 2 a 4 times cx plus d. Okay? But actually, I would like to distribute all these terms. Okay, number one, check this out. Like terms here, 2c plus 2c, y double prime sub p equals to 4c e to the 2x. And then I'm going to distribute all of this here. I'm going to multiply 4cx times exponential plus 4cx times exponential plus 4d times exponential. All right? So that is what's going to go into the second derivative. All right? Okay. Pause the recording. So looks like, yes, I forgot the d here, e to the 2x. Okay, so let's substitute into the differential equation. Okay, so, yes, so second derivative, all this madness here. 4c e to the 2x plus 4cx e to the 2x plus 4d e to the 2x, okay, that's just a substitution for the second derivative, plus, okay, plus 2 times, no, minus actually, minus 2 times, open parentheses, for the first derivative, okay? Open parentheses for, what did I do here? Well, actually, I kind of changed my mind for the first derivative. I'm going to distribute all this, you know? I'm going to distribute it. That'll be a plus c e to the 2x, okay? And here I'm going to distribute 2 times cx, 2cx, e to the 2x, and 2d e to the 2x. All right? Minus 3 times, okay? Minus 3 times the guess of the function, all right? Which is ax plus b plus, well, actually bracket, plus, no, actually, you know what? Again, to avoid having too many grouping symbols, I'm going to distribute the exponential cx and d plus cx e to the 2x plus d e to the 2x, okay? And let that be equal, not enough space, equal to 4x minus 5 plus, what was that? 6x e to the 2x. Okay, that's only the setup, okay? Let's, the rest of the problem, distribute, bookkeep, etc. Careful, I'm gonna try and go in slow motion as best as I can. Okay, so this is gonna be 4c e to the 2x plus 4cx e to the 2x plus 4d e to the 2x, and let's distribute the 2 here. Whoops, okay. Here, here, and there. Oh, one more. Whoa. Just multiply all of this by 2. All right, so that's going to give us what? Negative 2a. Negative 2a minus 2c e to the 2x minus 4 cx e to the 2x minus 4d e to the 2x, all right? Okay, let's do the distribution for the last group. Use a different color for that. Minus 3a, minus 3b, that, and that. Okay, so, oh shoot, okay, negative 3a x minus 3b minus 3c x e to the 2x, and I'm going to continue the line here, plus 3d e to the 2x equal to 4x minus 5 and plus 6x e to the, what is that, 2x, all right? Okay guys, yes, we have a monster here. However, a bunch of terms are going to get canceled, all right? Okay, let's cancel some terms. Number 1, I would like to highlight first that's going to help us a lot better, okay? Actually, so when you watch this video again, so you can see what happened, okay? A constant times the exponential, another constant times exponential, another constant times exponential, another constant times exponential. Do I have another one? Yes, right here. Another constant times exponential. So that's one, okay? What else do we have? Okay, here, okay, with a different color, we have a constant times x times exponential, another constant times x times exponential, another constant times x times exponential. Do we have any other one of those? I believe that's about it, right? Okay, let's see. What else do we have? What other nature of terms do we have? Before we... Yes?
Is that plus 3e to the 2x wouldn't be a negative?
Which one?
The last...
This one?
Yeah. Should be a negative?
Should be a negative.
This is like distribution.
Oh, yes. This should be a negative. You're right. You're right. Thank you. Okay, negative. So, can we use a different color for, okay. constants, negative 2a minus 3b. Those are the only constant terms. And one more color only for constant times x. All right? Okay, do we have any like terms? Actually, how about 4d e to the 2x minus 4d e to the 2x? They go away. All right, what else? 4cx e to the 2x with minus 4c e to the 2x. Do we have anything else? I believe that's about it. Okay, so, yep. Okay, so now let me group terms, okay, in accordance with their nature of the kind of terms. I know at this point, if I gave you just an example like you do, at this point you guys would freak out about what to do. I mean, just in terms of how to manage all these many different terms with that have many different natures. Okay, let me do, because what do we have? Linear, constant, linear times constant. So let's follow the same pattern. Okay, so for linear, the only linear we have is a negative 3ax, all right? So negative 3ax, okay? Plus, I'm going to open parentheses for the next term, which is just the constants. The constants will be, okay, what do we have for the constants? Negative 2a minus 3b, okay? Negative 2a minus 3b. And then now let me start with the linear. The linear times the exponential, which is, what do we have for the linear times exponential? Isn't that negative 3cx e to the 2x? And then a constant, where is it? A constant times the exponential. What's the constant times the exponential? That's going to be, okay, constant times exponential, that is 4c minus 2c, which is 2c, and minus 3d e to the 2x. And let that be equal to 4x minus 5 plus 6x e to the 2x. All right? So, this is how we're going to set our equations together. Okay, I'm going to set, okay, negative 3a equals to 4. Okay, so negative 3a equals to 4. That's a equals to negative 4/3. Okay, so there goes the first one. Number 2. What do we have? Constant terms. That is, okay, let me highlight with another color. The same color, actually. We highlighted the constants times the constant and set it equal to the other constant. I mean, not times the constant, I mean set equal to the other constant. That is negative 2a minus 3b equals negative 5. Well, that's one equation to unknowns. One equation to unknowns. And we already have the value of a. So negative 2 times negative 4/3 plus, or minus 3b equals to negative 5. Okay, so negative times the negative equals to positive 8/3. So that is negative 3b plus 8/3 equals negative 5. Now, subtract 8/3 from negative 5. All right, so that'll be negative 3b equals to, you can use your calculator for these guys, that's fine. That's equal to negative 23 over 3. And dividing both sides by negative 3, negative over negative is positive. The denominator becomes a 9. B, let me continue here, B equals to 23 over 9. All right? We're going to equate, okay, I'm going to use a different color for this. Okay, we're going to equate the coefficient of x e to the 2x equals to the coefficient of x e to the 2x. I'm using blue to color code this. Okay, so that's actually negative 3c equals to 6, and c equals to negative 2. All right, so we're getting there. Okay, let me kind of box the constants we're already getting. Okay, there's one more to do. Okay, equating the coefficient of the exponent of the exponential term itself. All right, but here is the thing: for the exponential term with a constant being multiplied with itself, we need to, well, we don't have it in our forcing function, but you can think of this as a 0 e to the 2x. All right, so that means we can now, let me highlight with this color. So highlight the coefficient of e to the 2x, let it equal to 0. Okay, and what is this? Okay, so this is 2c minus 3d equals to 0. But actually, since we already know the value of c, let me do negative 3d equals to, what is that? Negative 2c. So d equals 2/3 c, okay, and d equals to 2/3 times c, which is negative 4, and multiplying these together, d equals to, what is that, for negative 4/3. All right, and well, we already have all coefficients already, so what are we going to do here? Well, so we can go back to the form of y sub p. Let me use a different color for this. So y sub p. So what do we have? Okay, oh, we had it at the top. Okay, so ax plus b, that is a linear a and b, where a equals negative 4/3 x plus b, which is minus 23 over 9, plus, okay, what else do we have? Cx plus d, where c equals negative 2x plus d, which is actually also negative 4/3 e to the 2x. And now at this point, we should be good and write the solution to the differential equation, the general solution, I mean, which again, it's a combination of a solution to a characteristic equation, a homogeneous equation, plus some particular, which is what we got already. Okay, so that is, okay, the solution we have over here, c1 e to the 3x plus c2 e to the negative x, c1 e to the 3x plus c2 e to the negative x, plus the particular solution, which is what we have in green right here, actually minus 4/3 4/3 x minus 23 over 9 plus negative 2x minus 4/3 e to the 2x. Final answer. Okay, that's final answer.